What's up, everyone? I hope you guys are having a great day so far. It's Ben, and today we're going to be covering areas between curves. This is a topic that's taught at the end of Calculus 1 at some schools, but most of the time taught in the beginning of Calculus 2. And it's a topic that many students struggle with, from what I've noticed, because you must understand integrals and integration at a pretty strong level. And a lot of students at the end of Calculus 1 are just learning how to integrate, and it's still a very confusing topic. So that's why I'm here today to provide some examples and some explanation on how to set up these problems and how to evaluate the integrals. I'm going to be going about over 3 examples today, maybe 4, we'll see, and I'm going to be going over solving them step by step and explaining my thought process. So before we get into the examples, I want to explain why this works and where the formulas come from to find the area between two curves. So to start off, let's go ahead and just draw a generic graph. So when like such, right? This is the x-axis, the y-axis, and let's say we have a function f of x like this. We'll call this function y equals f of x, right? And normally, when we want to find the area underneath the curve, let's go ahead and just draw 2 arbitrary points. We'll call this x equals a and x equals b. And usually, when we want to find the area underneath a curve, we just draw a whole bunch of rectangles, an infinite amount of rectangles, and find the area underneath that curve, right? Like we've learned, like you guys might have learned in your Calculus 1 classes. This is what we're doing, right? And then this will calculate the area underneath f of x. But if we were to have 2 functions, like for example, if we had another function like this, we'll call this y equals h of x, and we calculate this integral, we'll be finding the area underneath this curve, right? With rectangles as such. And so, if we want to find the area between these 2 curves, what we're going to do is find the area underneath f of x by calculating an integral of f of x from a to b, and finding the area underneath the function h of x from a to b, which will leave us, so if we call this total area right here, area 1, and call this area right here, area 2, if we do area 1 minus area 2, it leaves us with the total area between them. I hope that makes sense, but it's not super important to understand exactly why this works. It's better to just understand the formula and just do a little bunch of practice problems in my experience. But I think it's really cool to see this, and it makes intuitive sense, right? How exactly we find the area between them, we're basically going to be calculating an integral from a to b of f of x, right? That's finding that whole area underneath here, and we're going to subtract it by the area of a of 2 underneath this red function, h of x. Oops. Oh, yep. Like this. And this will give us that total area. And we can actually combine this into one integral of just a to b of f of x minus h of x dx. So we'll basically just be evaluating one integral with one of our functions subtracted by the other function. And when we're doing this with functions of x, we can just think of it as the top function minus the bottom function, right? This top function, what in this case our top function is this y equals f of x. It's above the y equals h of x, right? So that's our top function, f of x, like you see, and our bottom function, h of x. And if we're doing this with respect to y, with a function of y, it's basically the same thing. If we have a function like this, so we have 2 parabolas and we want to find the area between here, we will be doing the integral from the same thing, a to b, it will be doing the right function, this right function, subtracted by this left function. Right minus left, like this. Don't worry too much if this is confusing to you. I'll be going over some examples to make this clear. But yeah, these are the formulas that you really want to remember. This is really it right here, just f of x minus h of x. Let's go ahead and jump into our first example. So in our first example today, we're going to be finding the area between the curves y equals x squared plus 2, the function y equals sine of x, in the lines x equals -1 and x equals 2. So let's go ahead and draw these functions out. It's not super important to draw them out. It helps you get a better visualization. It's not completely necessary, but in this case, I want to show you guys everything. So let's go ahead and draw these functions out. So for our first function, I'll call this y sub 1 and y sub 2, right? And so for our first function, we notice that it's a parabola, right? X squared. And that plus 2 is the y-intercept, meaning that we'll just go up 1, 2. This is our y-intercept. And our parabola will just look something like this. Pretty easy. We'll call this y equals x squared plus 2. And then the next graph is y equals sine of x. And sine of x starts at 0 when x is equal to 0. So we're going to go ahead and draw this now. It goes up to here, like this. It's oscillating. It's not so important on how accurate the graph is. But this is something like how it would look. And we also have the two other lines, x equals to -1 and x equals 2. So I'm going to use a different color here. We're going to draw the line y equals, or x equals -1, which is going to look something like right here. X equals -1. And the other one's going to be x equals 2. We'll just draw this right here. X, this is the line x equals 2. And so we're finding the area bounded by all these curves. That area that we're going to be looking for is this area in between these two curves. So remember, the formula is from a to b of our top function minus our bottom function. So in this case, it's pretty obvious what our top function is. It's the parabola x squared plus 2. And we're going to subtract it from the bottom function, which is just sine x. So we can go ahead and write this integral out. We're going to do our top, remember, top function, x squared plus 2. And then we're going to do minus, and let's go to do parentheses just to show that we're subtracting it from our bottom function, which is just sine x dx. But we need to find the bounds. And in this case, our bounds were already given to us, right? We're finding the area between x equals -1 and x equals 2. So that's pretty easy. Let's go ahead and write from -1 to 2. And let's go ahead and evaluate this integral. This is a very straightforward integral. There's pluses and minuses between everything, meaning we can just integrate straight across. So first term, x squared, reverse power rule. We add 1 to the exponent, divide by the new exponent. And we're going to, for the 2, we're just going to add an x, 2x, right? Because the derivative of 2x is 2, so that's why it's 2x. I want to do minus, and remember, antiderivative of sine is negative cosine, sorry. Right there. And since we have a negative and a negative, these turn to positives, right? We can FOIL that in, it becomes a positive. And then we need to go ahead and evaluate this from -1 to 2. Let's go ahead and move down here. Let's go ahead and plug in our top bounds now. So we're going to go ahead and get 2 cubed over 3 plus 2 times 3. Sorry, 2 times 2. My mistake. Plus cosine of 2. And then we're going to go ahead and do minus, and then we're going to go ahead and evaluate at the bottom bound now. So we're going to have a negative 1 cubed over 3 plus 2 times negative 1 plus cosine of negative 1. So simplifying this now, it's just basic arithmetic. 2 cubed is 8, so we get an 8 over 3 plus 2 times 2 is 4 plus cosine of 2. We're going to go ahead and just keep it like that. We don't want to simplify it, or we don't want to approximate it. And so remember, we have a negative 1 cubed. When we have an odd power, like 3, 5, 7, the number in the inside is going to stay negative, and 1 raised to any power stays as 1. So negative 1 cubed, an odd power, stays negative. So it's just negative 1. And so if this whole thing right here is negative 1, we're distributing this negative in, or actually let's say that for the last step, sorry. Let's go ahead and we have a negative here, and we're going to keep this as negative 1 over 3, remember, because it stays negative. And we have 2 times negative 1, giving us negative 2, and we have plus cosine of negative 1. Now we can go ahead and FOIL in this negative to all these, giving us 8 over 3 plus 4 plus cosine of 2. And then we're going to get plus 1 over 3, right? Double negative. And then we're going to get a plus 2. And then we're going to get a minus cosine of negative 1. So now we can simplify some stuff. We have common terms. 8 over 3 plus 1 over 3 is 9 over 3. We have 4 plus 2 is 6. And then this cosine and this cosine just stay the same. We don't want to approximate them. And boom, 9 over 3 is just 3. Plus 6 is 9. And then we get cosine of 2 minus cosine of negative 1. We can go ahead and simplify this one more time. It's not super necessary, but we can go ahead and just write 9 plus cosine of 2 minus cosine of 1. The reason why I just wrote it as 1 instead of negative 1 is because cosine is an even function, meaning it's symmetric across the y-axis. So if you plug in a negative input, you will still get the same y output. It's not super important for you guys to know that, but this is the final answer that I would submit in my class. And yeah, not too bad of an example. Let's get on to the next one. For our next problem, we're going to be finding the area bounded between the curves y equals a over x, the curve y equals 2x, and the line x equals 4. So let's go ahead and draw this out, because it's good practice, and some professors might prefer you or might ask you to draw out or at least sketch the function every time. So remember, it's not super important to be exact with your drawings, but let's just go ahead and do our best. So the line y equals a over x, we know that the function 1 over x has an asymptote at x equals 0, so we can just go ahead and draw a rough graph like this. It also has it down here. There we go. We'll call this y equals 8 over x. If you're not very confident with drawing graphs, either just take some extra time to study it, or you can just go on Desmos and play around and try to just recognize what each common function looks like on a graph. And so for the next line, y equals 2x is just a straight line like this with a slope of 2. It's not super important to be accurate. And then the last line we have is x equals 4, which is a straight line, straight vertical line at x equals 4. And that's going to be right here. This is the line x equals 4. And since we're finding the area bounded between these curves, that area is this area right here that I'm shading in. We want to find the area between these curves. So we just need to define our top function and our bottom function, right? So let's go ahead and set up our integral. And looking at this, our top function is the line y equals 2x, right? Which one is on top of the other one? Obviously, this line y equals 2x, right, is above y equals 8 over x. So that's going to be our top function. So we're going to go ahead and write 2x minus 8 over x dx. So we're almost done setting up the integral. We just need to find the bounds of integration now. We want to find, what that means is we need to find this x coordinate and this x coordinate. Well, we were already given what this x coordinate is right here, right? It's x equals 4. So this is x equals 4. That's going to be our top bound. But then we need to find this point right here. Since it's not given to us, we need to solve for it. And to solve for a point of intersection, we need to get those two curves and set them equal to each other and solve for x. So our two curves in this case, y equals 2x and y equals 8 over x. So we're going to go ahead and set up an equation and solve for x. So let's get our first equation. 8 over x equals 2x. And this is a pretty simple equation to solve. We're just going to go ahead and multiply x to both sides. Again, these will cancel out, giving us 8 equals 2x squared. Dividing both sides by 2, we get 4 equals x squared. And taking the square root of both sides gives us x equals plus or minus 2. But we only care about the plus, not the minus, because that minus is taking into account the intersection right here on this point right here. But we don't care about that. We only care about this area up here, which is the point x equals 2. So we only care about the positive 2, meaning that one of our point of intersection is at the x coordinate 2. The y coordinate is not so important, which is nice for us. We don't have to worry about that. We can go ahead and just write 2. So now we have an integral set up for us. Now we need to go ahead and take our time with it and evaluate it step by step. So this first part is 2x, antiderivative of 2x, x squared, then minus 8 over x. Remember, the antiderivative of 1 over x is ln of x. This 8 just adds a times 8 to it, giving us 8 ln of x. Now, evaluating it from 2 to 4 gives us 4 squared minus 8 ln of 4 minus, now our bottom bounds, we get 2 squared minus 8 ln of 2. Simplifying this, we get 16 minus 8 ln of 4 minus 4, right? And distributing this negative, we get plus 8 ln of 2. So, simplifying this further, we have common terms right here. We have 16 minus 4, which is 12. Then we have negative 8 ln of 4 plus 8 ln of 2. And that's our final answer. That wasn't too bad. Remember, what we did, we drew out our functions, and then once we drew out our functions, we needed to get the bounds from them. After finding out which one's the top function, which one's the bottom function, one of our bounds was given to us, the other one was not. So what we had to do was set up an equation where we set both of our functions equal to each other to find the intersection point, which what we did here. We ended up finding that it was x equals plus or minus 2. We disregarded the minus 2, and found that x is equal to 2. That's one of the intersection points. So that was one of our bounds. It was the bottom bound because it's the a point. Our bottom bound is the lower of the values, and the 4 was the higher of the values, which is why it's on the top. And then we just plugged in our top function minus our bottom function, found the antiderivative, evaluated it, simplified, and voila, that's our final answer. On to the third example. So the next example is going to be a bit different. We're going to be using functions of y instead of x. So our first function is going to be x equals y squared minus y plus 6 close x sub 1. And then our x sub 2, our other function, is going to be 2y plus 4. And so, since these functions are a bit more complicated, unless you're really confident with your drawing your quadratics and your parabolas and stuff like that, it's not necessary to draw these functions out. I'm going to go ahead and proceed and find the bounds and find the intersections between these two curves without drawing them out. So, recall what I said, set the equations equal to one another, and solve for them. So, we're going to go ahead and set up an equation. So one of our equations is y squared minus y plus 6 equals our other equation, 2y plus 4. And so solving for this, let's go ahead and get everything on one side and get 0 on the other. So we're going to subtract 2y from both sides. Now we're going to subtract 4 from both sides. This was supposed to be a negative 6. So scratch that, negative 6. I'm so sorry about that, guys. Negative 6. So subtracting negative 4 from both sides gives us negative 10. Now, we recognize that this is a quadratic. We have ax squared minus bx, or ay squared minus by minus c. And what we do here, to find out what values of y we need for this equation to equal 0, which is just solving for it, we're going to go ahead and try to factor this quadratic. So, using the diamond method, we want to find two numbers that add to our b term and two numbers that multiply to our c term. So we're going to find two numbers that multiply to 10, negative 10, and two numbers that, sorry, that's a 3. Two numbers that add to negative 3. And right away, we can see that it's 5, negative 5, and positive 2. Negative 5 plus 2 is negative 3, and negative 5 times 2 is negative 10, meaning we can write this equation as y minus 5 times y plus 2 equals 0. Now, we need to find what values of y will make this equation equal to 0. Looking at this first part, what would make this equal to 0? Y equals 5 would make it equal to 0, right? 5 minus 5 is 0. So one of our values is going to be 5. And looking at this other one, it needs to be negative 2, right? Negative 2 plus 2 is 0. 0 times whatever this is equal to is 0, meaning that our other value is going to be negative 2, meaning that this is our bounds of integration. This is where these two curves intersect. So now, that's the hardest part out of the way, I would say. So setting up our integral, we have our bounds from negative 2 to 5. And remember what I said earlier when we're doing functions of x, or functions of y, sorry, it's our right curve minus the left curve. In here, we don't have this drawn out, so in order to find out what's the right curve or the greater curve, we just need to plug in some value between our bounds into our functions and find out which produces a greater value. So we can just pick an easy number between negative 2 and 5, which is just 0. So we can go ahead up here, and for our x1, when we plug in 0, right, we get 0 squared minus 0 minus 6, which is just negative 6. And for x sub 2, when we plug in 0, we get 2 times 0 plus 4, which is just positive 4. And obviously, 4 is greater than negative 6, meaning that x of 2, so x sub 2 is our right function, our greater function. So that's going to be our right function. So we're going to go ahead and plug in 2y plus 4 minus our left function, our smaller function, which is going to be y squared minus y minus 6 dy. So let's go ahead and FOIL in this negative, giving us an integral from negative 2 to 5 of 2y plus 4 minus y squared plus y plus 6 dy. Now, combining like terms, we have this 2y and we have this y, and we also have this 4 and this 6. So let's go ahead and just write this in descending order. Negative 2 to 5, we have this negative y squared, and we have plus 3y, and we have a plus 10. Now, we can go ahead and integrate this very easily. Reverse power rule for the first time, we have 1/4 y to the 4th, right? We added 1 to the power divided by the new power. Then we're going to, remember, add 1 to the power, divide by the new power. And for this 10, we're going to go ahead and just add a y, or multiply a y. Now we have the balance from negative 2 to 5. Now, all we need to do is just evaluate our antiderivative at our bounds. So we'll go ahead and plugging in the first bound, this should be cubed, and dividing it by 3. So for our first one, we have negative 1/3 times 5 cubed plus 3/2 times 5 squared plus 10 times 5. And then remember, minus our bottom bound, minus parenthesis, always to keep it separated and clean. So we have negative 1/3 times negative 2 cubed plus 3/2 times negative 2 squared plus 10 times negative 2. Now, all we need to do, you can either pull out a calculator or just simplify this by hand. I'm going to just go ahead and simplify this by hand really quickly to find our final answer. So 5 cubed is 125. So we have negative 125 over 3. Let me write a better 5, whatever. Then over here, we have 5 squared, 25. 25 times 3 is 75 over 2 plus 50. And we have minus, keep the parentheses, we'll FOIL it in after. Negative 2 cubed, remember odd power, it's going to stay negative. So 2 cubed is 8. So we have negative 8. So we have negative 8 times this negative 1/3. So it's going to become positive 8/3. And over here, we have negative 2 squared, even power, so it turns positive. We have 2 squared, 4. 4 times 3, 12. So we have 12/2, and then 10 times negative 2 is negative 20. Now, we can go ahead and just distribute this, then negative n, giving us negative 125 over 3 plus 75 over 2 plus 50, and then minus 8/3 minus 12/2 minus 20. Sorry, this is supposed to be a plus 20, right? Negative times negative is plus. So now to simplify this, we just need to just do some simple arithmetic. Let's go ahead and just combine this 125 over 3 and this 8 over 3. So negative 125 minus 8 is negative 133 over 3. And then we have this 12/2, which just turns to 6. So we have 50 minus 6, which is 44, plus 20 is 66, or 64, sorry, plus 64. Now we have this 75/2 remaining. 64/1. Now, to add these all together, we need a common denominator. The common denominator between these three functions is going to be 6. So to get 6, we need to multiply this by 2/2 This one is multiplied by 6 over 6, and multiply this one by 3 over 3, which results us in negative 266 over 6, and then 64 times 6. Let's go ahead and use a calculator. 64 times 6 is 384. We have plus 384 over 6, and then 75 times 3 is going to be 225. So plus 225 over 6. Now adding these all up together, we get 384 plus 225 minus 266, leaving us with 343 over 6, which is our final answer. 343 over 6 is the area bounded between these two curves. And see, we didn't even need to draw out the function. Yes, it would help just to see it, but all we need to do is just find the points of intersection, find our right curve, subtracted by our left curve. And in this case, since we didn't see it, we just need to figure out what function produces a greater value for a certain x input. So that's it for that example. Let's go over one more example. In our last example, it's going to be a bit of a long one, but it's going to be a very important one because this is more of a challenging problem that you'll see in your classes where we'll need to compute 3 areas to find the total area between these curves. So our first function is going to be y equals 4x plus 3, y equals 6 minus x minus 2x squared, and x equals negative 4, and the line x equals 2. And since these are a little bit of more complicated functions, instead of drawing them out or attempting to draw them out, we can just use a graphing calculator. My favorite is to use Desmos, which is a great option. And so these are the graphs right here. And we're going to be calculating, since we're doing it from the lines x equals 2 to x equals negative 4, this purple line and this black line, we're going to be finding the area between this region right here, this region, and this small region between here. So going back to drawing it, now that we know what it looks like, I've went ahead and drew this problem out for you guys, or drew the functions out for you guys, so I didn't take too much of your time. But now, like I said, we're going to be calculating the area between here, the area between here, and the area between here. We're going to call this area 1, we're going to call this area 2, and we're going to call this area 3. So we need to go ahead and add up all these areas to find the total area, meaning we'll have to calculate 3 integrals. So for the first area, let's go ahead and find the area of this section right here. So we already know that our left bound is going to be negative 4, but we don't know what our top bound is going to be. We need to find this point of intersection right there. So like what we did last time, we're going to set up an equation where we're going to set up our graphs equal to each other. We're going to have 4x plus 3 equals to 6 minus x minus 2x squared. Doing some simplifying, now that we have our quadratic, we can go ahead and use the quadratic formula. You guys could try to factor this on your own, but I like to use the quadratic formula when we have an a value greater than 1. So remember, quadratic formula is minus b, so minus 5 plus or minus square root of b squared, which is 20. It's going to be 25 minus 4 times our a, which is 2, times our c, which is negative 3, over 2a, so 2 times 2. So this result gives us negative 5 plus minus 25 minus 4 times 2 is 8, So we have 8 minus negative 3, giving us negative 24. We have this negative right here, turns positive. So 25 plus 24 is 49. And then we have the square root of 49 over 4. Square root of 49 is just 7. So we get 5 over negative 4 plus minus 7 over 4. Now we can go ahead and find the x values using our plus and minus. So for our first x value, we're going to do negative 5 over 4 plus 7 over 4, giving us 2 over 4, which is just 1/2. And then our other one is going to be x equals, let me box this in. So we get x equals negative 5 over 4 minus 7 over 4, giving us negative 12 over 4, which is just negative 3. So those are our 2 points of intersection of this whole entire of these 2 functions. So obviously our negative value, our negative x, is going to be over here. So this point right here, our x value right there is negative 3. That's going to be our negative 3. And up here, when we need to find the intersection right here, that's going to be our 1x equals 1/2, which will be helpful for us later. So with that being said, our bounds are going to be from negative 4, which is from this point of this intersection right here, sorry, to this one, negative 3. And then remember, it's going to be our top curve minus our bottom curve. Our top curve in this case was 4x plus 3 minus our whole bottom curve. And now I'm going to go ahead and just skip through this and come back with the answer. You guys can take your time to solve this, plug this into a calculator, however you like. I invite you to try this on your own to practice your integration skills. And so after computing that integral, we found out that the area is 25 over 6. And this was our A1, so we need to keep track of that. On to the next area. So the next area is going to be this area bounded between the curves right here, this middle section. And we already know what the bounds are. It's from negative 3 to 1/2. So we can go ahead and set up the integral from negative 3 to 1/2. And then top curve minus our bottom curve. And in this case, our top curve is going to be the parabola 6 minus x minus 2x squared, and then minus the line 4x plus 3 dx. And now, like before, I invite you to try to solve this integral on your own, and I'll come back with the answers. But we've computed the integral. We found that the area was 343 over 24. We're going to go ahead and box that in and move on to the third area. And once we find this third area, we're just going to add up all the areas together, and that'll be our final area. So this should be, this is pretty repetitive now. We're going to go ahead and set up an integral for this third area right here. We already know what our smaller bound is. It's 1/2. The top bound will be from is x equals 2. Top curve is going to be 4x plus 3 minus our bottom curve, which is going to be 6 minus x squared dx. After solving this integral, we should have the area as 81 over 8. And this is our A3. So, like I said earlier, the total area is all of these areas added up together. A1 plus A2 plus A3. So, collecting all of our areas, our total area is going to be A1, which is 25 over 6, plus our area 2, which is 343 over 24. Plus our third area, which is 81 over 8. These all have a common denominator of 24. We can just get this fraction to have a denominator of 24, and this one to have a denominator of 24. So what we can do is multiply this by 4 over 4 times this one by 3 over 3. And this gives us 100 over 24 plus 343 over 24 plus 81 times 3, which is 243 over 24. Now adding up all the numerators together, we get 686 over 24, which we can simplify by just dividing the top and bottom by 2. Yes. And there we go. That's the final area, 343 over 12. That's the total area between all these regions bounded by the curves. So yes, that was a bit more of a trickier example. I think these these 4 examples, however, I forget how many examples I covered, but I think these examples are basically everything that you'll see. There might be some more challenging examples in your homework or in your classes, but with this information that you learned here should be enough to solve these to any problem that comes your way. And yes, that's going to be it for today. I hope you guys enjoyed this video. Make sure to like, leave a comment, any suggestions, anything you want me to post, any recommendations, or any just advice on my videos, anything that you think I could fix, or anything that you like about my video, just leave it down below. I'll be reading all the comments. Thank you guys for watching, and stay tuned.